Hello and welcome to Empowered Learning. This is the sixth and final video in the Laplace transform series where we cover the inverse Laplace transform and we see how we use that to solve ordinary differential equations. So in short, we know that the Laplace transform has an inverse operation called the inverse Laplace transform. And of course, we're going to denote it by this capital L here raised to the -1. And of course, the function that goes inside of that would be the big F of S. For our problems, we'll call it big Y of S, since we'll be solving our ordinary differential equations for little y of t. So of course, corresponding big Y of S would be in here. And the main thing that I want to get across, like I said in the part 5 video for this series, is that we do have this formula that actually defines what the inverse Laplace transform is, but we don't use this particular formula, okay? In all actuality, what we are actually going to do is we're going to use these Laplace transform tables that we have been using in the part 5 video, and I think for some of the earlier ones as well. We've been using these particular Laplace transforms, and this is just a basic one. I don't have one that is as extensive as some other tables, but for what we need to do here, this is the basic one. So we're going to use this Laplace transform table and basically say, if I can get something, let's say in this form here, then I'm going to say once I get it into this form, then the inverse Laplace transform of that is going to be this function here. If I can get something in this form here for Laplace transform, I know that I can say the inverse Laplace transform is this function here. So in essence, the thing that's going to be challenging here is, first of all, trying to get our Laplace transform expressions in a form to where we can look at the table and say, well, the inverse Laplace transform of this particular expression is this, which means we're going to have to do a lot of algebra. Okay, specifically speaking, like I mentioned in the part 5 video, we're going to have to use a lot of partial fraction expansion, and so we're going to see a whole lot of that. Now, some of the examples that I'm going to do here, I'm actually going to do the examples that we saw in the part 5 video, the examples A through E. And I'm going to run through all of them to show you how we actually solve those for y of t by using this concept of the inverse Laplace transform, like I just described. Now, the thing that I want to get at here is that some of these problems are going to be long, and they're going to be long on purpose, okay? Now, part of the reason why I'm doing these long problems is because I want you to see how when we solve some ordinary differential equations, it's kind of almost straightforward. We easily get the answer, we're done, okay? Other times when we do it, even though we're thinking that, hey, we can change our basically our calculus problem into an algebra problem, we're going to see that the algebra also gets a little intense and a little laborious. And so I want to show you that we can actually do the Laplace transform, use those techniques to be able to solve it. But you're going to see that after we do it, it's like, man, you know, that took a lot. I'm glad we got to the answer, but there has to be a better way to do this. And so fortunately, there will be. And so in my next video, which I'll start talking about the convolution operator, that will sort of be our way of saying, hey, you know what? I could use a Laplace transform, but I don't want to do all that algebra. Is there a way for me to get a hybrid in between doing calculus, pure calculus and pure algebra to get to these answers quickly? And of course, convolution will be the way to do that. And I'm going to take some of these examples that we have in this particular video and show you how we can actually do the same thing in that convolution video that I'm talking about, and show you how we could get the y of t solution to our ODEs doing it that way as well. So I don't want you to think that in practice that you actually have to do some of these long problems the way that I am doing, but I do want to show you some examples of that so that you get a feel for how it is. I also want you to see that in some of these cases, you're going to have to deal with complex factors. And so I want to make sure you know how to deal with that as well. All right, so let's go ahead and just get started and jump into this. So this first example, I've already worked out, so I'm just going to kind of talk through it. So we see here, this was our initial value problem for our first order differential equation. This is the actual answer that we got from the part 5 video as far as what the Laplace transform of our actual solution would be. And so if we were to do the inverse Laplace transform of both sides of this equation here, both sides of this equation here, then of course what we would just end up having is this. And of course the inverse Laplace transform of big Y of S, this is just going to be what Y of t is. Here we see that we have inverse Laplace transform of 10 over S times S plus 7 and minus inverse Laplace transform of 3 over S plus 7. Now, what I'm noting here is that we could actually figure out what the Laplace transform of this is pretty straightforward here, okay? Since it's easy to do, I'm going to wait to do it till the end, and I'm going to focus more so on trying to find the inverse Laplace transform of this situation here. So if we look at this expression here, and remember partial fraction expansion, we know that we could rewrite 10 divided by the product of S and S plus 7 as some constant divided by S plus another constant divided by S plus 7. And of course, if we use the cover up method, and this is a way for us to avoid having to basically do stuff like this. We don't want to do this sort of thing and, and have to go and, create systems of equations if we don't have to. So doing the cover up method here, we just basically say that A is going to be 10 divided by the denominator that A doesn't have, and then evaluating it at the value of S that makes the denominator that it does have go to 0. Okay. And B, same thing. B is going to be 10 divided by the denominator that it does not have, and it's going to be evaluated at the value of S that makes the denominator that it does have go to 0. So if we do that, then of course we see for A, once we plug in everything, we get a negative 10 over 7. And we see that for for A, we get positive 10 over 7. And for B, we get a negative 10 over 7. And so then we see that, of course, this expression here can just be rewritten this way. And of course, we see that this is just some constant times 1 over S. And we see this is another constant divided by, there's another constant times 1 divided by S plus 7. And so here we could take the inverse Laplace transform of this, which can be rewritten this way, factor out the common factor of 10 over 7, and then just find a Laplace transform of these two expressions here. So find the inverse Laplace transform form for the 1 over S. Of course, that is just 1. Because we know that the inverse, not the inverse, but the Laplace transform of 1 is just 1 over S. And of course, for the 1 divided by S plus 7, the inverse Laplace transform of that would be e raised to the negative 7t. And we know that because the Laplace transform of e raised to the alpha t is going to be 1 over S minus alpha, okay? And in this case, this is like S minus negative 7. So that's why our alpha here would be -7. So s minus a -7, s plus 7. So that's how we get the e raised to the -7t here. So once that's done, and essentially all we have to do is just put everything together. So for these first two terms, we see that it just ends up being this. And I'll go ahead and erase this just so that we don't have too much clutter. Now, if you remember, we still had a third term that the last term that we had to deal with, which was this inverse Laplace transform of 3 over s plus 7. And of course, if we factor out the 3, then this portion in here, the 1 divided by s plus 7, again, is just 3 times whatever the inverse Laplace transform of this is, which that corresponding function again is just e raised to the -7t. So we put that all together and we see that these two terms are like terms. So we combine those and we'll end up getting a positive 11 over 7 times e raised to the -7t plus 10 over 7. And so this would be what the actual solution to our first order initial value ordinary differential equation would be here. So just to be plain, if we were to take this particular function and plug it in, take the solution that we got, take the first derivative of it, plug it in, we would see that the left side here would also equal 10, provided that y sub 0 is equal to -3. So now we have example B. And so for this one, we see that this was the ordinary differential equation that we were working with in example 6B with the initial condition of y of 0 is 0. And we found that the Laplace transform of what the solution is supposed to be would look like this. Now, before we start on this one, one of the things that I want us to notice here is that we have this e raised to the -4s here, okay? And notice that this is with the Laplace transform. So if we take a look at what this looks like, here we have e raised to the -4s divided by this. And of course, we could think of this as just 1 over here times that. And notice that this is matching what we see here. Okay. So whenever we have e raised to the -s times alpha in the s domain, we know that that translates to a shift, horizontal shift to be exact, in the t domain, or the time domain, if we want to think about t in terms of time. So the point that I want to make here is that in doing this problem, we want to go ahead and account for this now so that we don't have to worry about it in the future. And then all that we have to be concerned about is figuring out what is going to be the Laplace transform of this, which is relatively easy to do. So if we come here, let's say that we want to find out what y of t is. Of course, that's going to be inverse Laplace transform of this. And here we know that this part here is just going to translate to f of this. And of course, it looked like this. So of course, our alpha is just going to be 4. And of course, big F of S, we're just going to call it this. And of course, F of T is going to be the inverse Laplace transform of big F of S. So we're just going to work on this we know that whatever answer we get there, we're going to have to apply a horizontal shift to that answer, and we'll be pretty much done from there. So here we know that if we were to take big F of S, which looks like this, and we could rewrite it this way to do partial fraction expansion. Of course, here, if we're going to find out what A is, using the techniques of the cover-up method, we'll just take our whole quotient here. And of course, since we're trying to find A, what we don't want here is S. So we multiply times that to make that reduce to 1. And we evaluate it at the value of S that would make the denominator that it does have go to 0. So essentially, what we have here is this situation where we have 1 over S minus 5 evaluated at S equals 0, which that will give you a negative 1/5. If we do similar thing for B, we'll see in this case that we need to get rid of the S minus 5 factor. And of course, the value of S that makes the S minus 5 go to 0 is 5. So that will reduce to 1. And I forgot to reduce these to 1 here as well. And so what this will end up being is just 1 over S, where S is 5. Of course, that ends up being a positive 1/5. So what that looks like for us here is big F of S is just going to be negative 1/5 over S plus 1 over 5 S minus 5. And I'm going to rewrite it this way. I'll factor out a 1/5, and we'll just say this is 1 over S minus 5 minus 1 over S. So now we need to find the inverse Laplace transform of this, which will just be F of t. Of course, we know that anytime we have 1 over S minus some real number, that's going to be related to a exponential function, and 1 over S here is going to be related to 1. And so I'll go to our tables here to show that. So we see here 1 over S, inverse Laplace transform of that is 1. And of course, 1 over S minus some real number here, inverse Laplace transform of that is e raised to the alpha t. So we could just say this is 1/5. And then, of course, if we do the inverse Laplace transform of this minus inverse Laplace transform of that, then that would just be 1 over 5 e raised to the 5t minus here 1. And notice that if we're looking at it in this sense, we know that our values of t are going to be greater than or equal to 0 in this case. And of course, we say that because by definition of Laplace transform, we're looking at values from t from 0 onward, and we're assuming that this particular function will be continuous and defined at t equals 0. So now that we have what little f of t is, we know that what we're going to have to do is do that shift, okay? So what we actually need to find out is what y of t is, which is just f of t minus 4. So our result here, y of t, which is f of t minus 4, what we would have to do in this sense here for this first term is, instead of writing t, we have t minus 4. Okay. Now for the second term, we could put a 1 there, but here if we did that, we would have to note that t is at this point going to be greater than or equal to 4. Okay. And so if we're looking at this particular term here, this is 1, but it only starts whenever t is greater than or equal to 4. If we draw that, then that's going to look something like this. Okay, and otherwise it's going to be 0 here. Now, if you say that looks familiar, then you're probably right, because it should look familiar. This essentially looks like our unit step function, but shifted 4 units to the right. So here, another way that we can actually write this, instead of writing 1, what we would have to do is write this as step 4, or step of t minus 4. Okay, so an alternative way we could write the result of this would be like this. And I'm going to write it like that so it's plain to see. And of course, again, t would have to be greater than or equal to 4 to make that happen. And so writing it like this, what this essentially does is it says, all right, it's letting us know that we're not even going to plug in values of t that are going to be less than 4. Okay, because if you have it like this, I really don't have to put this in, because of course this would be 0. And we know, of course, for the Laplace transform that anything that's going to make this be negative anyway just doesn't even matter. We don't even consider those things. So in general here, your final answer, you could express it this way, or you could express it this way. Okay, either way is correct. And so the only other thing I wanted to mention here is that we could also see how this could be the case by looking at our chart, because of course, if we went back here and said, all right, well, what's the inverse Laplace transform of 1 divided by s? Remember that 1 could be expressed this way. Okay, so we have 1 expressed that way. And if we look back at our Laplace transform tables here, you'll see that for the step function, that's exactly what we have. And you see here, alpha is greater than or equal to 0. Okay, so in this case, if we had alpha to be 0, then it's the same as just 1 over s, which matches what we have here. And so that's why we could have either used it this way or came here and used this form of it, and we still would have arrived at something that would work. Okay, so for our next example, we saw that we had this second order differential equation, y double prime plus 4y is equal to sine of 2t, with these two initial conditions here. Oops, sorry about that. Yeah, with these two initial conditions here. And we saw that the corresponding Laplace transform of our actual solution was this particular expression here. Now, we're going to solve this purely by doing Laplace transforms. okay, and using their corresponding inverse Laplace transforms. So in that, we're going to have to play what I call the algebra games, okay? So the first thing that we see here is that if we look at this 2 divided by s squared plus 4, and the s squared plus 4 is squared, if we look at our tables here, you're going to notice that I have nothing in my tables that address how to deal with that, okay? There's nothing in these tables that address how I deal with that. So since I don't have anything to address how I'm going to deal with that, I'm going to have to rewrite my Laplace transform expressions in a way to where I can actually deal with it. And so if I look here, I notice that this s squared plus 4 can be factored out to conjugate factors here, complex conjugate factors to be exact. So we know from algebra that the sum of 2 squares is exactly what happens when we take a complex number and we multiply it times its conjugate. Well, we can do the same thing here and rewrite this as s plus 2i times s minus 2i. And of course, this 2 divided by s squared plus 4 quantity squared here, we could rewrite it this way, which means that now we have 2 divided by s plus 2i quantity squared, and of course, the s minus 2i quantity squared all in the denominator there. So in seeing that, we know that this s squared plus 4, we could keep this way. What we could do is rewrite our Laplace transform to do the whole partial fraction expansion thing in this way, okay? So basically, this term here is going to end up being 4 different terms when we break it out, because we know that for partial fraction expansion, we could say something like this. Let's say if this is a1 x plus I squared here plus a2, we could do this. I'm not sure why my pen doesn't want to write the way I want it to. But we know here from partial fraction expansion, we're going to have to expand both of these terms out even more, because whenever we have repeated roots, we have to do a term where we just have the single linear root without it being squared. And then, of course, we got to do same thing with it being squared. So that's why you see a over s plus 2i here, b over s plus 2i squared. Same deal here, c over s minus 2i, and d s minus 2i quantity squared. And then, of course, for the last term that I originally had here, I split it up into 2 separate terms. And part of the reason why I want to do that is because I notice here that this s over s squared plus 4, that matches something in my tables here. See, this s over s squared plus something squared, that matches cosine of omega t. And so we know that there's not exactly direct, but a pretty straightforward way to figure out the inverse Laplace transform that term. Same deal with the last term. If we look here, we have some number divided by s squared plus 4. That could relate to sine. And of course, we'll have to do some algebraic manipulation. But once we do that, once we get this number and that number there to match, of course, this one would be that squared. We could say whatever that factor is times inverse Laplace transform of this is just going to be that factor times sine of whatever omega is, t. So these last 2 terms, we already kind of know how to deal with, okay? It's just these first 4 that are kind of challenging to us. So what we're going to do to try to shorten the process here, well, actually, there's two ways you can do it. The way that I'm going to do it this go round is actually going to be the longer way. And I wanted to do it this way just to showcase that, hey, you can do one or the other. In the other example that I'm going to do that's kind of like this, I'll do it the way that I was just thinking about, which is, I think, the shorter way. But basically what we're going to do is just set up our system of equations so that we can figure out what A, B, C, and D are here, okay? Now, an alternative way to do this is we could do that whole cover-up method where we use this particular expression here, and since the factors here go with B and D, we can do the cover-up method to find out what B and D are directly, and then after that, we can take that result and take what we see here, and we can rewrite it in this form as well, and just subtract both of these terms on both sides. And once we're done here, we'll see what's left. Do the whole cover-up method again after we do some algebraic manipulation, figure out what A and C are, and then from there, we'll have what all of our constants are. And then, of course, we can do the inverse Laplace transform of all 6 terms here. What we're going to do doing it the traditional way is that we're just going to set up the equations and we're going to find basically A, B, C, and D all at once. Okay. So we set up this process here. We know that these first 4 terms that are up here would have to equal what this equals, which is the same as 2 divided by s squared plus 4 quantity squared. All right, so we set that up. And of course, to get this big quotient here, we're just looking to see, we need to have a common denominator here. So we're seeing what each term is missing, okay? So of course, this first term, since this is just s plus 2i, it is missing another s plus 2i, and then of course 2s minus 2i's. So I put that in the numerator for it. For B, it's just missing the s minus 2i quantity squared, so I'll put that in the numerator for it. For here, we see that it's missing, the third term is missing s minus 2i as well as s plus 2i squared, so we put that in the numerator for it. And then, of course, D is just missing s plus 2i squared. We put that in the numerator. All that divided by s plus 2i squared times s minus 2i squared, that equals this. And so now we know since the denominators are the same, then that means that the numerators are the same. And now this is just a matter of multiplying all this stuff out and grouping it so that we can match up the coefficients and the corresponding expressions to that to what we would have over here, okay? So we start that process, and I'm just going to work on each term separately to multiply it out and see what that's going to end up being. So for the first term, A times s plus 2i times s minus 2i quantity squared, I'll go ahead and handle this first, which is going to be the s squared minus 4is minus 4. Whenever I FOIL it out. And then, of course, take that, multiply it times the s plus 2i, and I get this expression here. And of course, everywhere where I have I squared, I know that's going to be a -1. So a -1 times, understood, -1 here is going to be a +1. And of course, +1 times 8 times s is just 8s. So I know that. And from here, I just combine this +8s with this -4s and get a +4s here. And I know that that first term simplifies to this. Do the same thing for the second term, just s minus 2i quantity squared times b. Of course, we FOIL that out and then distribute the b across to all 3 terms. End up getting this, fairly simple. Third term looks kind of similar to what we had here in the first term here. We go ahead and FOIL this out. Then after that, multiply this result times s minus 2i, get this result here. And then, of course, simplify what we can. Where we have I squared, we make sure it's -1. You see we get something very similar to what we had before. And then, of course, distribute the c to all 4 terms here. And we get this result. And finally, the last term, d, of course, we just FOIL it out and distribute d to all 3 terms here, and we get this result. So now that we have all that information, we're going to take all 4 things here and just basically add them together. And so when we add them together, this is what it looks like. And I've grouped it in a way to where we can see things in terms of s cubed, s squared, s. Actually, we have s squared I and then s. And then we have just I by itself, and then s squared, and then si, and then constants. Okay. And so I go and I group them according to s cubed, s squared, s, and just constants. And of course, the I part, I'm just kind of ignoring that and throwing it into the actual value of the constant. That kind of stuff will kind of take care of itself later. So I do my groupings here. Of course, this 2 that you see here is really a 0s cubed plus 0s squared plus 0s plus 2. Okay. And so that means everything over here, this times s cubed is going to be 0. Everything times s squared also going to be 0. Everything times s going to be 0. And of course, all the constants, add those together, is going to be 2. And so now this is just a matter of solving systems of equations at this point. Since a plus c is equal to 0, we know that this quantity here is 0. So that's going to simplify our work a little bit. We also know that a would be minus c. We may need to use that, may not, but we'll see. So of course, here I wrote it as c is equal to minus a. And of course, what I did here is took the fact that, and I'll just rewrite it that way to kind of go along with my work. If c is equal to minus a, then right here I can plug in minus a there. And that's exactly what I did here. Plug that in, and I know minus a is going to be a minus 2a. And a minus 2a times 2 is a minus 4a. And you don't see that here, but and that's kind of what I have, but I went ahead and did an extra step here. So, and I'll write this out so that you can see it. So I have, what is it, minus 4ai, and this is plus bd here, equals 0. And of course, all I did was move the minus bd over to the other side. Make it look like this. And then of course, if I multiply both sides by a -1, I end up getting 4ai is just b plus d. So that's where this came from. Going back up here, we know that since a plus c is equal to 0, then of course, all this term here is just going to be 0. And if I divide both sides by 4i, I know that d minus b is equal to 0. Or put another way, d is equal to b. And so that's what you see me doing here. And then of course, for this last expression here, remember that c is minus a. So c is minus a. I know that b plus d is going to be 4ai. And so I put all that information in. and I see that both terms end up giving me a minus 16ai, which gives me a minus 32. 8i equals 2. And of course, when I do the division for that, I end up with a is equal to this complex number of minus 1 divided by 16i. Okay. So now that I know that a is a negative 1 over 16i, since c is the negative of a, we know that's going to be a positive 1 over 16 minus positive 1 divided by 16i. Okay. And then, of course, we do our back substitution here. Of course, because we know of all this, then, of course, b is equal to d. We saw that here. So we could solve for b. 4ai is equal to 2b because we got b plus b. Then that means that 2ai is equal to b. And, of course, if we go ahead and solve for a, so all of this just equals 1/8 here at the end of the day. And of course we know that because remember a is a negative 1 over 16i. So we're actually using that here. And of course this is the same thing as a here. And of course if we multiply all that, 2 divided by 16 gives us 1/8. With the negative, gives us negative 1/8, and these two i's reduce to 1. So with that, we know what b and d are. We know what c is. We know what a is. So finally, we know what our a, b, c, and d are. So now all we have to do is take our Laplace transform expression and break it out into the equivalent one with the 6 expressions, put in our resulting constants, and then figure out what's going to be the inverse Laplace transform of each of these. Okay. So moving on to the next page here, we're going to handle this first term. That constant, we're just going to pull that out and then just try to take the inverse Laplace transform of what's left, which would just be this. And if we go to our basic tables here, we'll see that this e raised to the I alpha t is going to be the inverse Laplace transform for 1 over s minus I alpha. Okay. So rewriting it that way, we see that since our alpha is a negative 2i, or sorry, a negative 2, I should say, then of course the alpha here is going to be a negative 2i, and then t, and of course all this works out, and this is what our resulting function would be. And notice that it is in a complex form. Okay, and we're going to deal with that later. So we see that for the next term, the negative 1/8 over s plus 2i quantity squared, notice that here what we're actually looking at is something that looks like this. So we're actually looking at something that looks more so like this, but notice that we have a horizontal shift to the left 2i units there. So if you notice what I'm saying up here, if I have the Laplace transform of something, but with some kind of shift in the s domain, that's the equivalent of saying e raised to the I alpha t times f of t in the t domain. Okay, so I see that and I notice that, hey, this is the same thing as just saying I want to find the Laplace transform of 1 over s squared, but this horizontal shift in the s domain can just be translated into this function here on the outside of the inverse Laplace transform. Okay, and of course the inverse Laplace transform of 1 over s squared is just going to be t. And again, if we look at our chart here, we'll see that 1 over s squared inverse Laplace transform of that is indeed t. So moving on to the third term, notice that this third term looks very similar to the first term. It's just that it's the denominator is going to be its complex conjugate. So we see that we do similar things, and what we will end up with is a similar result. Okay. So for here, we see that I take out the constant 1 over 16i, take the inverse Laplace transform of 1 over s minus 2i. Of course, the inverse Laplace transform of this is just going to be the e raised to the I alpha t. And we see that this is just basically the conjugate of this. And then, of course, we do the fourth term. We see that we can leave the 1/8 out. And again, this looks like Laplace transform of 1 over s squared, but with a shift in the s domain, a horizontal shift of 2i units. So that translates to an e raised to the I alpha t function on the outside of it. And of course, inverse Laplace transform of 1 over s squared is just t. So we see we have this result here. Now, we finally do the low-hanging fruit that we had, which is here we see that we can factor out the 3. And then, of course, what remains is a direct translation of the inverse Laplace transform of this particular function here. And again, I'll go to the charts here. So we see that if our omega is 2, then this translates inverse Laplace transform of that is directly cosine of, in this case, 2t, since our omega is 2. And for our next one, we know that in order to have this to be direct, this number here is going to have to be the same as this number here before it's squared. Okay, so I'm going to have to algebraically manipulate this to make this work. So to do that, of course, I factor out the 5. Since I have a 2 here, I have to force a 2 to be up here, but to even that out and still make it be 1, I'm going to have to multiply that times 1/2. So in saying that, I end up having another factor of 1/2 here, which means that I end up actually having a factor or a constant on the outside of 5/2. And then, of course, this portion here, I take the direct inverse Laplace transform of that, and that's just sine of 2t. So now that I have all 6 terms done, I go ahead and write everything in. So this is what our first term was, second term, third term, fourth term, fifth term, sixth term. And so now I try to do some grouping here. Of course, these last two are pretty much done with. There's not much else I'm going to be able to do with that for now. I notice here that I have 2 terms where I have my denominator of 16i, and I have 2 terms that have a denominator of 8. And so what I'm thinking about here is that although I know this is complex, I remember that my Euler formula, let's say, I'll say e raised to the ix, we know that that's going to be cosine of x plus I sine of x. And of course, if I had this minus here, then the only thing that would be different is that this would be minus. And we know if we do the correct linear combinations of e raised to the ix and e raised to the minus ix, we could rewrite this in terms of sine. We can rearrange everything to find out what sine of x and what cosine of x is. And so that's the setup that I'm trying to do here. So here, if we remember, sine of theta is going to be e raised to the I theta minus e raised to the minus I theta over 2i. And of course, cosine theta is going to be e raised to the I theta plus e raised to the negative I theta, all that divided by 2. And so I see that if I let my theta be 2t for both of these, then I know that this expression here would just be sine of 2t and cosine of 2t respectively. So here what I'll see is that all of this will just be sine of 2t, and all of this will be cosine of 2t. And so when I replace that, I end up with 1/8 sine of 2t, minus t divided by 4 cosine of 2t. And of course, I got my last two terms here. And then from that point, I can combine like terms. Okay, so I know these two terms are going to be like terms, and I know these two terms are going to be like terms. So I just combine them together, and I see that my result here ends up being y of t is 21/8 sine of 2t plus 3 cosine of 2t minus 1/4 t cosine of 2t. Okay, and for here, even though these are like terms, I wrote them differently since this one actually had the t cosine of 2t in it. And if you remember, whenever we solve these types of ordinary differential equations, this would be the equivalent of my y of p, and this would be the y of h, where this would be my c2 and this would be my c1. And of course, we got that automatically because we already had the initial conditions already baked in the problem. Okay. Now, again, I told you before that this problem was long, but I did want to show you how we deal with these things whenever all that we have as far as tools are concerned is the Laplace transforms to deal with. Okay. Now, I do realize again that this probably would have been much more simple if we would have used method of undetermined coefficients for this, or variation of parameters. For those of you that are familiar with the convolution operator, we could use that as well to make this problem a little short. Okay, but again, if we were using just pure Laplace transforms, this is how it would look. All right, so let's look at our next example. I know the last one was a doozy. This one will be too, because again, I want to show you what this looks like if we use pure Laplace transform information to be able to solve these problems here. And so hopefully some of the other methods that we've learned before, you have an appreciation for it. But also I want you to see the cases when Laplace transform actually, takes longer than doing some of those other methods. And again, the Laplace transform is just a tool. There are times when using that tool is a convenient thing to do. There's other times when using that tool is not so convenient. And again, that's what I'm trying to demonstrate here. All right. So for this next example, another second order linear non-homogeneous equation where the force function that we have here is one to where we could use method of undetermined coefficients, but we're going to use Laplace transform to do it. So we were given that our Laplace transform of the actual solution ends up being this expression here. And so I had already talked about in the last video how we could change this s squared minus 4s plus 13 to be this s minus 2 quantity squared plus 9. And so from here, the point that I'm trying to make in saying all this business here is that we're trying to be able to take the inverse Laplace transform of each of these terms. So if I was to come here and say this is s minus 2 squared plus 9, the problem again is that I don't have anything in my current Laplace transform tables here that tell me how to deal with some quadratic expression squared. Okay, so you notice here I have quadratic expressions here, but they're not quadratic expressions squared. And if you notice, this is the only thing that comes close to that, but I would have to have something inside of here that's linear for me to be able to use it along with the shifting property that we're used to seeing. Okay, So if you notice here, nothing that I have here in this table tells me how to deal with the quadratic expression squared. And of course, the expression that I'm talking about here that lets me know, hold on, let me go back. Yep, so yeah, that was the wrong one. So the one, yeah, this is the one I was looking for right here. So we have some kind of shifting property in the S domain. So that lets us know that, hey, we can just multiply whatever our actual Laplace transform of this base function here is times e raised to the alpha t. So we don't have anything like that. So we're going to have to factor down even more to get it where we can actually use that table. So I'm doing all this business here to say s minus 2 squared plus 9. I found out what the complex conjugate zeros are for this particular expression so that I can factor this down into linear factors, okay? And so you see that once I've done that here, I'll have s minus 2 is just a number because s could be a number. Right now it's acting as a variable since it's in a Laplace transform. But of course, we could put a number into it. So we have real part minus imaginary, and all that squared, times real part plus imaginary squared. And so this is what we need to be able to use the Laplace transform tables to be able to get our inverse Laplace transforms. So we're going to take what we know here and we're going to rewrite it. Same deal here. So we know that expression here, the s squared minus 4s plus 13 quantity squared, all that can be rewritten this way. And of course, the s squared minus 4s plus 13 just simply factors out to what we see here. Factors out this, which again factors out to that. So what I've done is just got everything looking linear, okay? And yeah, I think I was pointing at the wrong thing here. So this expression here, these four expressions are covered by it. This expression goes with this one. This expression goes with that one. These two, we know this one is going to be some, when we do the inverse Laplace transform, is going to be cosine of something with some kind of shift. And this is going to be sine of something with some kind of shift. So these two are relatively easy. It's these four that we have to battle with. And what we're going to do this time is actually use the cover-up method. And so the cover-up method says that we're first, since this term here consists of these four terms, and we actually have these two factors here, we're actually going to find out what B and D are first, and then rewrite these four terms, have it equal to that. We're going to rewrite it so that we'll get an expression for A. This plus that will equal to what's left over on the other side of that equation. And then we'll do the process again, okay? So we start off, we take this expression here. And of course, if I want B, then what I do is I say this is going to be 3 divided by the denominator that it does not have. And I'm going to evaluate it at the value that makes the denominator that we do have go to 0. Okay. And I'm going to do the same thing for D. So notice 3 divided by the denominator that I do not have, evaluated by the complex number, in this case, that will make the denominator that I did have go to 0. And so I go in, plug in all that information here, and I see that I end up with a negative 1/12 once I do that. I do the same thing for D. Do 3 divided by the denominator that I did not have, evaluated by the number for S that makes the denominator that I did have here go to 0. And I see that I also get a negative 1/12 there. So from that point, we realize that the first 4 terms of my Laplace transform y of s is going to be equal to these 4 terms here, where this is b, that is d. And so now my goal is to basically add both of these terms to both sides so that I have this by itself. And I'm going to have to rewrite this once I add both of these terms to this side. So I go ahead and I do that here in this step. And then, again, I'm just going to try to make like denominators so that I can figure out what my numerator is going to be. And what I'm expecting to happen is that since I have a divided by s minus 2 minus 3i and the conjugate of that here, whatever I have in the numerator, I should be able to have a factor of s minus 2 minus 3i times s minus 2 plus 3i, so that this expression on the left side here, when we put it all together, is going to simplify to basically be something divided by s minus 2 minus 3i times s minus 2 plus 3i. So that's what we are expecting, and that's what we should get when we do this. So we go ahead and take whatever it is that we're missing for both of these terms here. So for this term, it is missing the s minus 2 plus 3i quantity squared. So if you notice here, that's what I put in the numerator for here. This one is missing this denominator, so I multiply the the positive 1/12 times that. And of course, that's what I have here in the numerator. So from there, I multiply everything out. And so we've seen this kind of thing before, so I'm not going to spend a whole lot of time talking about it now. But we've basically multiplied this out, so we FOIL this out. And then once we FOIL it out, we try to cancel terms to 0 and then combine like terms as much as we can. And you're going to see once we actually do all that, what we end up with is this expression here. And of course, if we factor out a 2 out of 18 and the 2 that's out of this, we end up getting 2 times, in parentheses, s squared minus 4s plus 4 plus 9. Okay. And of course, we've seen this before. Okay. So if we come here, these first 3 terms here, come on, pen, please work for me. These first 3 terms here is just s minus 2 quantity squared. And then, of course, we have the plus 9 from over here. So we see that this is s minus 2 squared plus 9, all of this. Okay. Now, of course, we know that s minus 2 squared plus 9 is also this s minus 2 minus 3i times s minus 2 plus 3i when we factor it out. And so that's kind of what we're looking for here. And so we see, because we know that, we can rewrite this way. We have one of the factors in the denominator for each one of these will reduce to 1 with these factors here in the numerator. And what we effectively have here, once we do all the simplification and everything, is just 1/6, and that just comes from 2 divided by 12 here. And of course, all that kind of came from just the manipulation from up here. Just to be clear, going from this step to this step, I had multiplied the numerator and denominator by 12. Okay, So that's how I ended up getting the 12 in the denominator here. And of course, 2 divided by 12 is the same as 1 divided by 6. And then of course, I just brought the 1 divided by 6 as just a fraction in the numerator here. So once I'm here, then I see that, hey, I got a constant times this product here. And this is already set up to do the partial fraction expansion via the cover-up method. So we just do the cover-up method one more time, okay? So A is just going to be 1/6 divided by the denominator that it doesn't have, evaluated at the value of S that makes the denominator that it does have go to 0, okay? So we evaluate that till we get 1 divided by 36i. Do the same thing for C. And we see that we end up getting a -1 over 36i. So a lot of hard work, but we finally got there. And so we see what our A, C, and B, and D are. So we have all 4 of our constants. So now we can just throw them into what our Laplace transform expression is going to be. And so we went from having 3 expressions to now 6. These were the last 2 that we originally had. And these 4 came from the big one that had the 3 divided by, was it the S minus 2 squared plus 3i squared. And then of course the same thing here, minus 3i squared. Okay, so all that was what these 4 terms end up being. And so now, just like how we did last time, we're going to take each of these and take the inverse Laplace transform of them. Okay, so looks very similar to what we did in the previous example, so I'm not going to spend a lot of time going over it this time. Of course, we take out constant here. We see that this is a Laplace transform of a complex exponential function, where the shift here just means that we can multiply our little f of t times e raised to the alpha t. We see here for this case, we have a linear expression, even though it's complex, it's still linear, squared. So we look at this and we say, hey, first thing I could do is I have this shift in the S domain. So I could take this and translate it as e raised to the alpha t for the inverse Laplace transform of it. And so that just simplifies to the S. This ends up being linear. And so here we know that this is another time shift. So not time shift, but S shift. So horizontal shift to the right 3i units. So I can think of this as just 1 over S squared, where again I have that e raised to the I alpha t this time. Before this shift here gave me real valued exponential function, whereas this shift here gave me complex valued exponential function. And so of course inverse Laplace transform 1 over S squared is just t. And of course what this result ends up being here is very similar to this one, just a conjugate of it basically. And this example here, basically the same process as this one, and actually we end up getting the same thing for it. And then of course our last 2, again we have that horizontal shift in the S domain. So here, notice that since this is one where it has an S on top, that's going to go along with the one for cosine, okay? And so here, if we have a shift down here that looks like this, then here I'm going to have a matching S minus 2 up here. Okay. Now, if I'm forcing that to happen, if I have a minus 2 here, I'm also going to have to do a plus 2 so that this is equivalent to what that looks like. So in seeing that, that is the reason why you see me here in this expression. I went ahead and factored out the 4, and this s becomes s minus 2 plus 2. And so now I break this up into 2 separate expressions where I need to take the inverse Laplace transform. For this first one here, these shifts match, so that once I take into account for that shift by e raised to the 2t, then here what I end up seeing is that, hey, this is just essentially the inverse Laplace transform of cosine of 3t. For this term here, we have 2. So once we take care of the shift here and make that e raised to the 2t, we notice here that I need a 3 in the numerator, okay? I already had a 2 here, so I'm actually going to make sure that that gets pulled out. And here, to make this be the equivalent of 2, and I need a 3, I got to have a 1/3 here, so that 1/3 times 3 is 1. 1 times 2 is 2. So it's the same. So we're going to take all of this and pull it out, leave the 3 in. So that's where we get the 2/3 here. And of course, 3 divided by s squared plus 3 squared is just going to be the inverse Laplace transform. When we do the inverse Laplace transform of that, that's just sine of 3t. And of course, this first term is just cosine of 3t here. Both of these have a 4e raised to the 2t in it, so I just factored that out and just left everything else that was in there. And so now, once we kind of combine everything together, we have these two terms here. And so we see that doing the inverse Laplace transform of this actually yields me 2 terms here. And then for our last term, again, we have that shift in the s domain. So once we factor out the negative 13 here, we force this to look the way that it needs to. Since I have a 3 here, I got to force myself to have a 3 here, but I need this factor of 1/3 here to kind of balance it out to make it be 1 like it's supposed to. So I take that 1/3 and pull it out. And then what I have here is essentially going to be sine of 3t, but with a shift. So I take care of the shift. And then after I take care of the shift, I'm finally to where I can just say, hey, the rest of this is just sine of 3t. And I end up with my expression there. So finally, we put all this together. And we see, just like how we had in example C, that we have some of these terms that have complex exponential functions to them. And we're going to use same linear combination of Euler's equations or Euler formulas to be able to rewrite that in terms of sine and cosine of 3t in this case. So you see that we do that here. So of course, this term together, we combine those, factor out 1/18 to get it into the form to make it be sine of 3t. Of course, here, these two terms, we factor out 1/6. What's left here ends up being cosine of 3t. And of course, everything else just looks the way it's supposed to look. Yeah. And these two terms here are like terms. So that's what ends up making this be negative 5/3 e raised to the 2t sine of 3t. And so now we have everything that we need here. So technically this is our answer, but here all we're doing is just simplifying, okay? And so once we simplify everything, we see that this ends up being our final result. All right, so now we are at our final example. And so I wanted to close out this particular video with a third order linear non-homogeneous ODE that we can solve, because I wanted you to see something a little different. Most people, when they solve these, they do everything up to the second order. Kind of wanted to do a third order one so you can see the difference in how you would handle that versus those that are second order and a little crazy. Okay. So we see here that, of course, our Laplace transform was these two terms here added together. And we talked about in previous problems where we were dealing with this, the previous video where we actually solved this particular, well, we didn't solve it, but we got the Laplace transform equivalent of what the answer is. And we said that we were going to decide, hey, are we going to keep this apart or put it together? And so we're going to go ahead and put it together here because you're going to see the method we're going to use is going to be that cover-up method again. But once we do what we can with the cover-up method, we're just going to do algebraic manipulation to figure out what our remaining constants will be in doing that whole partial fraction expansion process. So we note here that s cubed minus 27 is just the difference of cubes. And we know that because s cubed minus 27 is just going to be s cubed minus 3 cubed. So we know that. And I'll go ahead and write that here. So this is s cubed minus 3 cubed. And so, of course, this factors out where we have this irreducible quadratic factor that can only be factored into complex numbers. And another way that we could rewrite this is using completing the square. And so that's what I'm doing here. And we can rewrite it this way. And we want to rewrite it this way because if we ignore this part, then the denominator will look like s squared plus another number squared. And of course, we know that this is what our denominator for what sine and cosine of omega t look like. And so we want to keep our denominator in this form when convenient, so that when we do the inverse Laplace transform, we know that it's tied to one of those two trig functions. So to get our y of big Y of s into one quotient here, we know we need to make like denominators. Since both of these denominators are the same here, we know that the one thing that's missing, well, both of these factors are the same here. The s plus 3 is the thing that's missing. So we need to multiply numerator and denominator by s plus 3 of the second term. And so if we put it together, and of course, multiply these two things together, we'll get all this business here. And of course, that simplifies to this in the numerator. And so now we can say that all of this can be rewritten as these three terms here. So a divided by s plus 3 plus b divided by s minus 3 plus cs plus d, all that divided by the irreducible quadratic factor there. And we just got it written in completing the square terms, so that when we do the inverse Laplace transform at the end, we'll know that it's either tied to a sine or a cosine function. So we're going to do the cover-up method to find a and b. And so we're going to do the cover-up method to do that because relatively easy to do. Once we're done with that, since our numerator here is a two-term numerator, what I'm going to do instead of kind of breaking this out and trying to figure out what C is, or what D would be in this case, and then turn around and try to redo everything to do C, I'm just going to go ahead and stop it at that point and do the algebraic manipulation. And so I'm saying that because we have 1, 2, 3 factors here. So I could technically do the cover-up method to find A, to find B, and to find D, and then plug all those in and then rewrite everything and then just find out what this constant c would be at the end. But I think it'll be a little easier if I just go ahead and do a and b and just start it. We'll kind of see how it goes. So I'll start off with a, and of course a is just going to be this whole quotient here, where at the end of the day I want a to be everything here, but the denominator that I do have, that's the thing that needs to go away. So the denominators that I don't have is the s minus 3 and all this business here. So a is just going to be this whole thing without the denominator I do have, evaluated at the value of s that would make the denominator that I did have go to 0. Okay. And of course, this is what the expression would end up being. And we'll go ahead and put this here. And then from that, of course, we plug in all the numbers, do all the number crunching, and we see that we get negative 1/54. So we do the same thing for b. Of course, s minus 3 was the denominator for the b term in the partial fraction expansion. So get rid of that. Result here, everything that the b term didn't have for the denominator, we keep that and evaluate it at the value that the b denominator would have had to be able to go to 0. And then of course plug in all the numbers, do the number crunching, we get 187 over 162 for b. So after that, we see that our quotient here is just equal to these two terms here with the a and the b in. And of course, our goal is to get this by itself. Okay? So once we do that, then it's just a matter of a bunch of algebraic manipulation to get it to where we need to be. Now, the main thing that we want to make sure that we remember is that in order to get it in this form, notice that what's over here has this extra s plus 3 times s minus 3. So when I add this term to both sides and subtract this term to both sides, and I combine everything together, what I should be able to get once I'm done is a result here to where the numerator has factors in it of s plus 3 and s minus 3. Okay, so once we get everything consolidated, we're going to act as if that's the case. And then of course, if what we have here is correct, we'll see that that actually falls out, and we'll be able to find an equivalent expression on the left side of this equation that can match up with the right side here, with what's circled here. Okay, so we add this term to both sides, subtract that term to both sides. We have that here. And then it's just a matter of trying to group everything and get it together. So here I know for this particular term, I am missing the s minus 3 and this quadratic factor here. So I multiply those two factors to the numerator here. And for this one, I'm missing the s plus 3 and the quadratic factor. So I multiply that. Now, I remember that s minus 3 times all this business here. Remember, this is the same as the s squared plus 3s plus 9. And this times that was just s cubed minus 27. So we remember that, and that kind of makes what we're doing here a little bit more simple. Unfortunately here, that doesn't reduce down to anything, so we're actually going to have to multiply that out. And so you see that I have that result here. So I've also went ahead and taken the time to write the equivalent fraction for this because I want to try to simplify, and I want all the fractions to have the same denominator, and that's going to help me out. So once we're at that point, then I'll multiply everything through, and then from this step to the next one, what I'm basically doing is just grouping all the terms in the numerator. So all the terms with s cubed, all the terms with s squared, all the terms with s, all the terms that are constants, grouping them. And so you see me doing this here. And again, I am grouping it in such a way to where the result, I wanted to keep it as something divided by 162 because I think that will help me be able to do some easy reducing later on. So I'm at this point here, and now I'm going to multiply the numerator and denominator by 1, but I'm going to make 1 look like 162 over itself. So when I do that here, then of course that's going to clear out all the fractions. And of course I have 162 on bottom here. And I got something that looks a little bit more tamed. And I notice here that all of my coefficients are even. So I know that I can factor out at least a 2. It turns out that I can factor out 4 out of each of these. So I do that. And of course, the 4 and the 162 reduce to 2 over 81. And so then at that point, I'll go ahead and move this 2 divided by 81, move that fraction up to the top. And I am at the point where I am saying whatever I have here should have a factor of s plus 3 and s minus 3 in it. And so we expect that because we know that if this side has to equal, the left side has to equal the right side, then we know that whatever's going on here, it's going to have to go away, okay? Which means that the only way that can happen is this numerator would have a factor of s plus 3 and s minus 3. So what we're going to do is use synthetic division to factor down this polynomial of degree 3 to get it to where we need it to be at, okay? So we take the fact that, of course, if s plus 3 and s minus 3 are factors, then we can use s to be plus or minus 3 in our synthetic division. So we do it the first time with s equals 3, do our synthetic division here. And we see, of course, that we get 0 in the remainder box, which lets us know that s minus 3 was indeed a factor of our expression here. And I don't know why that says this. Yeah, so I don't know why that's there. I'm going to cross that out and actually put the correct thing. And so this should be 35s cubed plus 84s squared minus 315s minus 756. So that's what it should be. So I must have been looking at like another problem when I wrote this down. So anyway, so we do the synthetic division here. And we see that when we do it the first time, we get 0 in the remainder box. That's what we expect. We carry this quotient over and do the synthetic division again with the minus 3. And we see, of course, again, we get 0 in the remainder box, which is exactly what we were looking for. And so this lets us know that our expression here factors down to s plus 3 times s minus 3 times, and then whatever's left here, this is a linear factor, 35s plus 84. So now that we have that in place, we can rewrite our numerator as everything that we just stated up here over s plus 3 times s minus 3 times the quadratic factor, and that has to equal this. We know the s plus 3 and the s minus 3 have to reduce to 1. And if we, from there, take the 2 divided by 81 and multiply it to both terms there, we'll get 70 over 81 here, 168 over 81 there. And of course, we can easily see from this that this is what C is, and that's what D is. So we have what our C and D are. Remember, we already found what A and B are. So here we are on the home stretch here, now that we have all of our coefficients. And so we go and throw those back into the partial fraction expansion version of our Laplace transform of our ODE. And of course, from this point, we just look at the tables, figure out what the Laplace transform of each term is. The first two terms are relatively easy. We know anytime we have some number divided by s plus or minus a number, we know that relates to an exponential function. So this will end up being e raised to the minus 3t here. This will end up being e raised to the positive 3t once we look at our Laplace transform tables. So for this term, of course, I factored out the 70 divided by 81. But what I did here is I split this up into two separate terms. So I looked at it, of course, the one with the s, because I know that's going to relate to something with cosine, and the one here with just a number, which I put down here, that's going to relate to something with sine. Now, because I have this shifting going on to the left by 3/2 units in the s domain, I have to mimic that here in the numerator. So I have to have this plus 3/2. But in order to balance it out to actually make it still be s, I have to subtract the same thing that I added. So that means I'm going to have to introduce another term. So I'm going to have another term that kind of looks like this. And that's going to combine with what this is going to end up being, because basically both of these, if we look at the inverse Laplace transform of them, are going to relate to some sine function. Okay, so we see that those first two terms, we went ahead and wrote those in. For the second term, notice that we went ahead and split it. And of course, in splitting this, I had to split it again. So we have the s plus 2 here, s plus 3/2 here, and of course, same deal here. And we're dealing with that minus 3/2 there. But of course, in order to make this work, the number that's inside of here has to also be up here. So I put it there. But since this is the thing that I forced, I have to multiply times the reciprocal of that to make everything balance out. So that's why you see all that stuff up there. For this term here, kind of the same thing. I needed this particular number here to be in the numerator. So I have to multiply times the reciprocal to force that to balance out to be 1. So once I do all that and pull out the factors that I need, then of course, I know what remains here is just cosine of 3√3/2t. And of course, I'm not done with this one because I got to pull all that stuff out. So once I get to this one, then this will be sine of 3√3/2t once I get there. Okay. So again, first terms, second terms, this particular term here, now that I got it into a form to where I can just concentrate on the shift in the s domain, I know that translates to multiplying the inverse Laplace transform function by e raised to the whatever the minus alpha, well, was e raised to the alpha times t. Okay, and since this is plus, this is like minus a negative, so that's why that ends up being negative here. And of course, we collapse the s plus 3/2 to just be s, and now this looks the way that we want it to. And this would be cosine of square root of 3/3, square root of 3 times 3/2. Okay. And of course, we already have addressed this one. And then, of course, the very last one here, of course, we've already said that, hey, this is going to be cosine of root 3 over 3, root 3 times 3 over 2. Okay. And so now it's just a matter of putting everything together. So we combine all like terms here. And of course, no, it looks kind of ugly, but I mean, once we're at this point, we're like, yeah, we're finally done. So we see that we have two sine terms, as I told you we would probably have. And so, of course, all we have to do is just add these two numbers together, and we get the 182 times square root of 3 over 242 for that one. Cosine here goes there. And, of course, we have these two terms that we've been carrying for a little while. And so this is our final result.